Well, Henry, thank you very much for that wonderful lecture, which I think was splendidly intelligible. We have lots of time for questions.
If I did a bit quick.
I can see a hand there. Do please stand up when you ask a question so that we can capture you on camera. Yes.
Thank you.
And if you would like to, say who you are.
My name is John Bell. It's a very simple question. How efficient is chlorophyll at converting solar energy?
Well, that was what I presented at first. So in terms of quantum efficiency, in terms of taking a photon of light and converting it to some usable form, it's very close to 100% efficient. But in terms of power conversion efficiency in a plant, it's less than 1% efficient. So it's not very efficient at producing energy. It's not. We need to coat a vast area of our land. If we wanted to use plants to produce power, we'd have to use a very much larger area of land than we do using electronic devices, photovoltaics.
The answer rather confuses me. How does that compare to what you're doing?
These technologies...
Is chlorophyll really brilliant? Or?
No. Chlorophyll, unfortunately, is very good at what it does for a plant, and it's obviously evolved over millennia. But in terms of usefulness for producing usable power for human use, it is not anywhere near as good as photovoltaics.
I think there's a question towards with a pink shirt. Yes.
Thanks. Peter Corley from Imperial College. I'm interested in the geographic spread of these things. So fossil fuels have given countries like this a huge advantage because we've had coal and oil and so on. With a large population density and not that much land, you're in really bad shape, and in northern latitudes, you're in very bad shape for solar. So you're talking about a huge shift of economic advantage to the south and to desert areas, obviously, as you describe in Dubai. What prospects can you hold out for Northern Europe?
Well, I slightly disagree with that because the cost of generating power is the cost of the installed PV, and that is coming down and down. So at the moment, it makes total sense in very sunny places. The UK, for instance, compared to Dubai, we get about 2.5 times less sunlight, but it's not 10 times less. So if the cost of installing a solar farm in Dubai is 2.8 cents or 3 cents per kilowatt hour, it'll be something like 8 cents per kilowatt hour in the sort of latitude that we are here. So it's not orders of magnitude more expensive. So that means as it goes down in price, the cost of generating actually very soon, within a decade, will be cheaper than producing electricity from coal, even in the UK. Now, in terms of storage, you store kilowatt hours, you don't store unit area. So the cost of storage, you'll require less storage in Northern Europe per square kilometre of PV panels. But of course, the cost per watt will be just the same. So actually, I think the continuing improvement in efficiency of industrial PV and reduction in cost will make it totally economic anywhere in the world to produce PV power. The opportunity is not necessarily where the resource is, but who enables that technology. Which countries have the companies that are developing and deploying the PV and in essence driving the whole power industry. So that's where the wealth, if you like, and the economic strength will come from. It'll actually be having the companies or the countries have the countries having the companies which are commercializing this and driving the industrialization. Now, at the moment, a large fraction of the silicon PV is in Chinese companies, and that's exactly where these new opportunities, for instance, with this sort of perovskite technology or other new clean energy technologies, actually give an opportunity for a different country to gain dominance in that area. So it's by no means sealed up. At the moment, the PV industry is probably a few % of the size that it'll be when we reach terawatts PV generation. So the companies of today are very small compared to the companies in a few decades' time. So even if they're geographically in China mainly, there are also a number in the US. It doesn't mean that's where the final dominant companies will end up.
Can I just
I'm not disputing any of that. I suppose my question is really about land area.
Yeah.
Because land area per person here is very small, and clearly, with the best will in the world, it is a low density power source.
Well, I did a back of the envelope calculation, so that is all this is, which I'm about to quote. But actually, this wasn't my calculation, but the amount of land per person in the UK that's farmed is about half the land mass. So we've got about 4,000 square meters per person per capita, and about 2,000 of that is farmland. I calculated that at 20% efficiency, to produce all our power, so electricity and our current power generated from burning fuels and transport, we need something like 100 square meters per person. So it's not insignificant, but it's on the order of 5% of our farmland or something like that.
Just to put a fly in the ointment, we do have winter as well as summer.
Yeah.
And it's about sort of 7 times less sunlight in January than in July, isn't it, Henry?
I refrain to say no comment. No, very
prerogative, yes.
very good point. So, I mean, of course, it would be better to have more sunlight, and it'd be very good to have good relationships in Europe so that we can have power cables coming up from Spain, etc., and not have to bicker over import tariffs on electricity.
Yes.
That wasn't my final point.
I'm not very good at spotting in which order the questions came. I could see Cyril. There's a question at the back there. It's always harder to see people at the back. But I'll come back.
Hi, John Bassett here from UK Power Networks. So obviously the PV is you installed it, but before that you've got extraction of resources from mining, and after you've got recycling. So I wonder if you give some comments on silicon technology and also new technologies and how it impacts those two aspects as well. Thank you.
Yeah, I mean, I think that there are a number of examples in the past where there's been some, for instance, bad pollution from slurry from soaring silicon put into rivers, etc. And that's not good, obviously, for the industry or for anyone. And it takes away largely from the benefit of PV. So the whole life cycle analysis has been done and is implemented on installed PV modules. They do get recycled, or there's a mandate to recycle them, and certainly any new technology being deployed will be recycled. So that has to be costed in. For instance, First Solar, which is one of the companies that deploys cadmium telluride solar cells, cadmium is not a very nice material, and they do recycle their modules. It costs about 2 cents, I believe about 2 cents per watt peak is the cost addition due to recycling. So it's something that has to be costed in, and they may be more or less fixed prices, so they're sort of a baseline price of what's required. Now, in terms of absolute energy input, for instance, in silicon, the ingots have to be made by heating to a few thousand degrees for tens of hours, and it's a lot of energy that goes into it. One of the selling points for our new materials are that they're processed, we don't heat them beyond 150 degrees, and they're dried very quickly. There isn't this long thermal input. That's easy to make that argument, but silicon has scaled so much, the ingots are made at such a scale, actually per wafer the energy input's relatively small. So you can overcome a lot of things that look like fundamental cost barriers simply by scaling, and that's something we've learned from many industries, but certainly the silicon PV industry is a very good example of that. So it'd be very easy for me to stand up and say we've got less energy input, we're going to be the much better, superior technology, but at the end of the day, if you scale enough, the cost per unit goes down and the real input per unit goes down. So it's very real. It's not just economics. It's
so one of the measures for that is how many years or months does it take collecting electricity from an installed solar panel to repay the energy that was used to make it and install it. For silicon, it's what, 18 months now?
It's depending on where they're installed, it can even be down to a year. So, yeah.
So long as it's sort of working for 25 years, a year is a fairly small upfront carbon dioxide penalty. Cyril, towards the front.
Cyril Hilson from a variety of organisations. Congratulations, not just on your lecture, but also on your research progress, which has been quite admirable. I'm interested in stability. I've worked with cesium and haven't found it to be the easiest of materials at times. I wonder if you can give us a number for where we've got to at the moment on half-life.
I can't give you a precise number. What we work for is these IEC targets, and for silicon PV, when they have 3,000 to 5,000 hours on these accelerated measurements, they're happy to stamp them with 25 years warranty. We're working towards 2,000 hours at the moment. So we've surpassed 1,000 on many tests, working towards 2,000. So we're on the route. But the other important note there is until you've actually got a full-scale module that's produced on a production line where you're not doing it at a research scale, let's say, you can't properly test these things, and it's likely that you will have introduced more errors than you would when you've got a very well-controlled process with very well-controlled deposition of layers in these devices. So we're expecting it to be there when we manufacture it, as we currently stand. But obviously this is a key consideration and something we really have to demonstrate and prove and gain confidence of the people who are going to be manufacturing it and deploying it.
Well, I'm used to being pleased when the efficiency is the same tomorrow as it was yesterday, so
yeah.
I congratulate you.
There's a question there, and there is one right at the back, so it will come. But let's start with a question towards the centre, 2/3 of the way to the back.
Thank you. Feel humor a question from a non-scientist. So in relation to the question about mining, I've heard a lot about global sand shortage and sand piracy. Now, I'm not a scientist, and I don't know if that's where you get your silicon from, but in terms of the ecosystem, in terms of the supply that was hinted at before, as well as any comments around superconductors, so how to get your electricity or your company's electricity to its consumers, if you maybe just provide a few comments.
So I'll answer those two questions. Firstly, about shortage of sand. I can't. I mean, I've never heard anyone complain there's a shortage of sand compared to the amount of sand that we use in building construction. Making glass. I mean, glass is 4 millimeters thick, 4 to 6 millimeters thick. Silicon wafers are a few hundred microns thick. I don't think sand shortage is going to be a problem for PV. So, I mean, there is serious concern over some rare earths like tellurium that's used in some solar cells. But again, these fears for elemental shortage are usually not very well founded, and it means they may not be being produced at a suitable level currently, but when there's the demand, we can go out and mine them. And currently there's enough stuff in the Earth's crust that we can make PV for many, many thousands of years. The other question, I've forgotten what you asked now, actually.
Just about superconductors.
Oh, in terms of for long-range power transport. For that, I presume you'd need a room temperature superconductor. This is something that's still elusive, but would be a great innovation, and people are working on towards these. I don't know if you've got... But that's not for long-range power. That's if you wanted a superconducting cable. For long-range power, you can use high-voltage power cables.
Well, and I would add that high-voltage DC is about 5 times more efficient than AC. I mean, the quoted figure is 5% loss per 1,000 kilometers for high-voltage DC, and that's been made possible through advances in high-voltage electronics that make it possible to switch voltages at DC voltages from silicon carbide, gallium nitride. It's all possible. So I
thank you.
away. Yes.
Right, thank you.
It's very likely that certainly within Europe, political instability aside, that we should easily be able to have a reinforced grid that enables transmission of electricity throughout from sunnier places to northern climates.
Okay. As an economist, the answer that supply will create or demand will create the supply is quite satisfactory. So thank you for that.
There was a question right at the back on this side.
Suzanne Wallace. I'm a PhD student over at Imperial. I had 2 quick questions, if I can be a bit cheeky. So firstly, you said that your modules are about 6 inches. Why is that?
No.
And I really would assume if you're printing, you could have any size you want.
Because we're processing on silicon, we're scaling up the manufacture of perovskite on silicon. Silicon wafers come at 6 inches in size. That's how big the ingots are and how big they're diced to. So that is industry standard. So we're not going to try and reinvent that. That is what current silicon industry wafers are. And one reason is for monocrystalline, that's how big they make these single crystals by pulling them out of a big vat. And if they go bigger, you can grow bigger crystals, but they are more likely to have faults and defects in them. So this turns out the ideal size for yield. In terms of assembling into the solar cell, having cells this size is also quite a good way, again, of improving yield, because the bigger the cell, the more likelihood that you'll have a critical failure on it. So the silicon industry started at 4-inch, went up to 6-inch, and it may be there for a long time. We're not going to try and change that. We're just processing on top of that. Ultimately, in an all-perovskite technology, if we do away with silicon and just try to make a thin film module that's perovskite, then yes, that could be any size. You still have an issue that you've got to manufacture on that size and get high yield.
Is it almost like your Christmas lights situation where one bulb blows and then they all blow? And whereas if you've got them in smaller sections, you have less of a problem?
Yes.
My second small question, if I may, was related to your tandem technologies. So obviously it seems that they are a much better technology than a single junction in terms of getting high efficiency quite quickly. But do you see the cost increase for that type of architecture? Is that significant enough that it may be difficult to balance that with economy of scale? And if there's a big increase going from 2-terminal to 4-terminal? I
mean, this is so if I just sort of discuss on the case of putting perovskite on silicon, the cost of the current silicon cell is about half the cost of the assembled module. And then when you deploy that module is about half the cost of the total installation. So there's something called balance of systems, which is the cost of the frames, the electronic inverters, the land, the permits. And that costs actually more than the cost of the module. So your cost of your cell is maybe a fifth of the total cost of installed PV. Now, so there's some room, therefore, if you're increasing the overall power output, to increase the cost, but you wouldn't want to treble it or quadruple it. So it has to be a small fractional increase, and it can't be much more expensive, but we don't think that will be. On the thin films, there may well be a market for a very inexpensive product that is just a single junction perovskite cell, but it's probably not utility scale power generation.
Okay, there's a question towards the front. There we go.
Thank you, Professor Henry. It was a very good lecture. I am part from India, CSR NPL. We have lots of our solar power. The question is, going from 24% to 31%, what are the limiting factors that you see in efficiency improvement?
To get there,
yeah.
A lot of it is optical, making sure we absorb enough light in each layer or the right amount of light. And then there's electrical. We still have losses between the absorber layer and the charge extraction layer, so the contacts we put on the absorber layer, there are losses. The charge recombines. We lose energy at those contacts. So that's where there's space to improve these things.
Okay, we're generating quite a few more questions, so let's move through them. One to the left there, my left. Yes.
Sure, I'm Ben Martinoga, a science journalist. So you've talked a lot about utility scale generation, but some people see a solar future where truly distributed power, so it's on every building material, clothes, devices. Do you see perovskites playing into that? Is that part of your vision?
Yeah, they certainly have a prospect there. So we've focused on the high efficiency tandem cells because we think that's where where the current biggest market is, so more of a commercial decision. In terms of building integration, one thing we have been working on is making these single junction perovskite cells semi-transparent. So instead of absorbing all the light, you actually allow a fair amount of the light to pass through. Of course, the efficiency drops because you're absorbing less light, but then these could be a replacement for glazing It's something that is probably going to come in the industry. It's called, as you no doubt know, it's called building integrated photovoltaics, where you actually basically use the PV in the building facade. That has been an industry that's been promising to grow for the last decade, and it hasn't quite taken off. Now, there is legislation coming in place in Europe that's going to mandate new buildings having, much less energy usage per square meter, and even reduce carbon impact. And this, one way to do that is to produce electricity in the building. So I'm sure we will see this. The timeline is difficult to predict. This technology absolutely could do that, and that probably wouldn't be the perovskite on silicon. That would just be the thin film perovskite. One advantage there, or one disadvantage with wafers, is that they are 6 inches, and you can see them when they're on a panel. People are implementing means to make them more discrete, but basically they're there. And if you don't want your building to look like a satellite, which lots of people don't, some people quite like it, then you want something else. You want just a thin film glass glazing. And that's what the thin film option can deliver.
A question over there.
My name is Yasser Hassan, postdoc from University of Oxford. I have a question for you, Henry. You have shown the periodic table, and you talked about alternative ways of combination between atoms. As a chemist, when I play with these parameters or these combinations, what's the characteristic list? When I checked, I will reach the moment. I say, I got it. What are these characteristics that I am looking for when I check all of them? I said, I got the beautiful materials that the whole world is aiming for.
This is an interesting question that I hadn't asked Yasser to ask me. So Yasser is one of my postdocs in my research group. One very... I'll reel off a prepared answer to this. One very important question on materials discovery is, how do you test those materials to see what they're useful for? And we'd love to have a machine that we could just mix these compounds together, stick them in the machine, it tests them in a gazillion ways and tells us this is a good superconductor, this is a PV material, this is a good solar cell material. Unfortunately, that doesn't exist, but what obviously does exist is metrics that we can use. And one metric for solar cell materials, which someone not used to working in it will find this quite ironic, is that luminescence, how much light emission these materials give when you shine light on them, is a very good measure of how good a solar cell material it is.
Okay, question at the back. 2 questions at the back, but one at a time. No.
Simon Dowland, University College London. Your talk covered mostly, for the new technologies, perovskites, but there are a number of other technologies which are competing for that space. Mm-hmm. And I was just wondering if you'd like to comment on where you see organic photovoltaics in relation to perovskites, particularly in regard to the fact that in recent years they've pushed through the 10% barrier. Mm-hmm.
So one of the sort of critical measures that's become apparent, especially over recent years, to deliver high efficiency is low electronic disorder. And you know how this is measured. I won't go into how it's measured, but basically this is how ideal your semiconductor is. Now, a semiconductor, not like organics, but amorphous silicon, which is the non-crystalline form of silicon, this has a large electronic disorder. And this means the maximum efficiency those solar cells can ever generate is about 13%. It's what they're at. They'll never get more than that. And because crystalline silicons come down in price so much, that's never going to compete for utility scale. Now, organics have continued to deliver on improvements over the last decade and still continue to deliver. And this electronic disorder, fundamental disorder in organic semiconductors, is actually not that high. It's quite low. They're quite ordered, which means the prospect for high efficiency is very good. And what that means is that it's really low electronic disorder equals a high voltage generated from your solar cell. And we're seeing increased voltages in organics. So they're probably not going to be a silver bullet, but I expect them to continue to improve. And as long as they're continued to be worked on, then they will eventually also probably rise to high efficiency. The other advantage of organics is you can tune the color. So actually for building integrated PV, they could also be quite interesting, where you can absorb in the infrared only.
You can take one last question at the back there.
So one last from non-science guy. I consider all of this course very interesting, but I see, have you ever considered that is the easiest way to get 30% of efficiency? For example, across my house, I use the typical photo installation with the 22, 23 at max on the solar trackers. And so you can cross the 30% of efficiency quite well and without the laboratory. So the question is maybe that the trackers is the future of the photovoltaic installations. Thank you.
I think so. If I just reiterate your question in case anyone didn't understand it, you were suggesting, and rightly, that as well as having a fixed axis, you can also track the sunlight. Of course, it doesn't improve the efficiency, it improves the energy yield, so the amount of power you extract, which will make it equivalent to a 30% efficient cell. I absolutely agree. In fact, we've done these calculations and seen exactly that. Of course, the higher efficiency the cell is, the more sense it makes to use trackers because you've got more power from the module, so you gain even more. So it offsets that additional cost. So actually, perovskites delivering a 30% flat plate technology, of course, on trackers would outperform your silicon. And it's likely that for many installations, at least single-axis tracking would be the preferred means because the efficiency is higher.
This is a rider to the last question, is it?
So the next question is, or the last
one?
Not
the next question.
Yeah, the last one. What we can do with the temperature, because when we exceed the 70%, 70 Celsius, we are out of game. So the question is what we can do with that.
Yeah. So the easiest answer is we'll make our cells 85% efficient, then we extract all the energy and we won't get temperature thermal gain. Of course, that's easier said than done. The more efficient they are, the less heat will be generated, but you're only talking about a 5% difference. This is something we have to, the better the technology and the better the contacts, the less recombination, the less losses at the surface of the material, the better the performance under higher temperature. So you see that all different technologies have a different temperature coefficient, how they lose efficiency on temperature. So that's about improving the technology as much as something it is something we have to live with. That's what has to go into the calculation of energy yield. But that is calculated, that's implemented when working out how much power you'll really generate in a different location. So that's actually an advantage of the UK, is the efficiency or the energy yield per absorbed watt will be higher than in somewhere like Dubai because the cells will be cooler. They actually operate better under cooler conditions.
Thank you. It's for the moment to draw the event to a close. And I want to start by thanking Henry for a wonderful lecture that was wonderfully accessible and has generated that real excitement that there are new prospects, that what in some ways had been seen as an old industry that was settled has been blown apart by these remarkable recent results. I would like to put that in a sort of scientific context. I mean, those who were in the will remember the early days of the world of germanium and then silicon will recall that we had to do something called zone refining to take impurities out of silicon down below 1 part in a million. Silicon devices don't work if they have chemical impurities at higher levels than maybe a part in a million. The materials Henry has discovered have got impurities at the level of several per hundred. And this is absolutely remarkable. You can take most textbooks on inorganic semiconductors and put them in the bin because Henry's materials, and this is a major discovery, are fault tolerant. They don't generate these defect states that you referred to, Henry, for amorphous silicon, non-crystalline silicon. Why they don't is a real surprise. There are some explanations. I wouldn't say there are yet complete explanations, but it has, I think anyone rationally on the basis of half a century of development of inorganic semiconductors picking up a material that, as you show, you cheerfully take some little piles of orange powder and white powder, and it goes black when you mix them together, and you do it on the lab bench. No one would have suspected that it would make a good semiconductor. And it's that sense of the utter unexpectedness of what you've discovered and and then how quickly that has translated into this fabulous opportunity that makes this so special. So it really is a wonderful moment to celebrate what you've done. I have some things to hand to you. Let me start with a medal. So Henry, can I...
Thank you very, very much.
And a scroll.
Thank you very much.
And then the one thing you shouldn't lose.
Thank you. Thank you very much.